Here we have the alternating series of -1 to the n dividing by n plus 1 factorial, and we want to show that this alternating series converges absolutely. And once again, to show that a series converges absolutely, we must put the absolute value around this expression right here and show that it still converges. And so we need to show that if we put absolute value around the expression -1 to the n dividing by n plus 1 factorial, and we need to show that this right here converges. So that's what we need to show. Now, the only difference between this series, alternating series, and this, the absolute value made a -1 become 1, positive 1. And so we can rewrite it like this. So the absolute value made this become 1. Not the limit comparison test, but the direct comparison test. And so again, to use the direct comparison test, so we want to show that this series right here converges. And then we need to come up with a series B sub n and show that the series B sub n converges. And so here, to show that this series right here converges, we can let A sub n be 1 divided by n plus 1 factorial. And here we can let B sub n be 1 divided by 2 to the n. And so no. N plus 1 factorial is greater than or equal to 2 to the n. When n is 1, we get 2 here. 2 factorial is 2. And when we get 1 here, we get 2. But when n is 2, this is 3 factorial. When n is 2, we get 2 plus 1 is 3. 3 factorial is 6. But 2 to the second is 4. And when n is 3, this is 3 plus 4. 4 factorial is 24. And 2 to the third is 8. And so this is true for n greater than 0. And so we came up with the series B sub n. And and then now we need to show that the series A sub n is less than B sub n. And so since n plus 1 factorial is greater than 2 to the n, now we do the reciprocal. We get this. So this would be less than or equal to this. So again, n plus 1 factorial is greater than or equal to 2 to the n. Now we do the reciprocal, then we have to flip the inequality sign. And so this means that the summation here is less than the summation 1 over 2 to the n. So this is series B sub n, and this is series A sub n. And so we have shown that series A sub n is less than B sub n. Now we also need to show that the series b sub n converges. And so we know that this is the same as 1/2 to the n. And this is a geometric series with common ratio r equal to 1/2. And since r is between -1 and 1, this series right here converges. By geometric series test. And once again, the geometric series test says that if we have a common ratio between -1 and 1, then the series converges. And so we have shown two things. We've shown that the series a sub n, which is 1 divided by n plus 1 factorial, is less than the series b sub n, which is the series 1 over 2 to the n. And then we have shown that the series 1 over 2 to the n converges, and therefore this series right here. And so by direct comparison test, the series converges. And therefore, remember that for this problem, what we wanted to show was this right here converges absolutely. And so one more time, to prove that this alternating series converges absolutely, and then what we have to do is, so to show that this series converges absolutely, we have to put absolute value around the expression -1 to the n dividing by n plus 1 factorial. But once we did that, the -1 becomes just 1 because of the absolute value. And then we have to show that this series converges. And we have just shown that it converges by using direct comparison test. And therefore, now we can say that the series, the alternating series -1 to the n dividing by n plus 1 factorial converges absolutely.